Hi, this is Laura Szymanski from Edina High School, and today we will be looking at Lesson 12, Properties of Logarithms. The opening exercise asks us to use the approximation of log of 2 to find the values of each of the following log expressions. So we do have to continue to use some of the properties we've learned. I can rewrite log of 20 as log of 10 to the first times 2. And we learned in Lesson 10 a couple lessons ago that the log of 10 then is just 1, and I can add it to the log of 2. So this warm-up just does a bit of review because they told me log of 2 is 0.3010. I can conclude that's 1.3010. So we go through and we just finish this up. So this would have been log of 10 to the negative 1 times 2. Same idea, except it's a negative 1 plus log of 2. When I added those, I got negative 0.6990. And finally, if we have for log of 2 to the 4th, that is the same as log of, I could write it as 2 times 2 times 2 times 2. So I can write it as log of 2 plus the log of 2 plus the log of 2 plus the log of 2, which actually reminds me that I have 4 of them, times the 0.3010. So you may have remembered a different property to help you with that. Okay. So the next step of this lesson introduces us to or reminds us of all of the properties we've learned and a couple more. So it asks us to explain why each statement is a property. Okay, so if I have log 1 equals 0, a lot of times I'll just rewrite it in exponential. It's base 10 because 10 to the 0 power equals 1. The second one, log of 10 equals 1. Well, that's because, again, if I rewrite it in exponential form, my base is 10, and 10 to the first power is 10. Property 3, for all real numbers r, log of 10 to the r equals r. Again, if I rewrite it, the base is 10, so I would rewrite it as 10 to the r over here, and it's equal to this 10 to the r, and those are in fact true. So again, these aren't formal proofs, but it's just using rewriting as in exponential form for those 3. And now number 4, when I have exponential form, I'm actually going to rewrite it in log form. So I would write log base 10 of x, so that's of this x, and it's equal to the exponent, which in this case is just log of x. So you can see I get the same thing on both sides. Now number 5 and 6, property 5 and 6 that it asks us to prove here are a little more in-depth. But if we follow the same property and rewrite in exponential form, this would be 10 to the log of x plus the log of y equals that x times y, what I'm taking the log of. In order for me to do this one, I do have to remember a property of exponents, and that is anytime I have the same base times each other, I add the exponents. So since these exponents are being added, I could break it apart as multiplication with the same base. So that requires some prior knowledge to be able to get there. And then if we go back to our previous slide, so number 4, we learned this property. If I have 10 to the log of something, but virtually the 10 and log cancel, and so our answer is just what I'm taking the log of. The reason I remind us of this is because here I have 10 to the log base 10 of x, so I would say those away. Same thing here, 10 to the log base 10 times y. So you can see I get the same thing. So these ones are a little more tricky. When I look at the next one, same idea. If I take it and rewrite it in exponential form, I would have base 10 to the r times log of x equals log of x to the r. Oh, no, that's not true. Sorry about that. It's just equal to the x times r, or x to the r. So it's just equal to what we're taking the log of, x to the r. Now this next one that I'm going to look at is I need to remember that I can move this exponent to the top. So because right now the 10 and the log aren't right next to each other, so I change it to 10 to the log of x to the r. And now that the 10 and the log are right next to each other, my answer is just what I'm taking the log of, which is x to the r. So you can see that those are little explanations as to why those 6 properties work the way they do. But the job of this chapter or this section is to now use those properties to solve some different things. And in this case, so make sure you're reading the directions carefully so you know what's expected of you. Here it says apply properties of logs to rewrite as a single log. So what that means is right now I have 2 logs in the question. I need to rewrite it as 1. First thing I'm going to do is using the property that we just looked at, property number 6. The first piece is starting as r log x. I can rewrite it as log of x to the r. So I'm going to take that first piece and rewrite it as log of 25 to the 1/2 plus log of 4. Now just some side work here. 25 to the 1/2 is the same as square root 25. So that's going to be 5. So I rewrite that as the log of 5 plus the log of 4. And then again, we looked at properties, and if we look at property 5 above, if we have 2 logs added together, we can combine them as a single log by multiplication. So this is log of 5 times 4, so my final answer is log of 20. You could just skip the step where I wrote log of 5 times 4. That's just to show you where I got it. So that's kind of the process we use on these problems when we are writing a single log. So we need to know those properties well in order to be successful. Try B and C on your own and then check your work here. For B, I did log of 8 to the 1/3 plus log of 16. And then I know that this is the cube root of 8, which is 2. So I rewrote it of log 2 plus log 16. And in this case, again, I know that I do log of 2 times 16, so it's the log of 32. Last but not least for this section, I would do log of 5 cubed plus log of 8. Excuse me, log, 0.8, sorry. 5 cubed is 125 times 0.8. Multiply that together, and I get log of 100. And I like this example because it shows me that I can't just stop here. 2 things, either we're asking what power of 10 is 100, and I know it's 2, or I could rewrite it as log of 10 squared, and then that property, I remember that it's just the exponent as the answer. So sometimes you won't have any logs when you use these properties. So that's the first type of problem you need to be able to do from this section. The second says apply properties of logarithms to rewrite each expression as a sum of terms involving log x, log y, where x and y are positive real numbers. So we're virtually going to take this and break it apart into multiple logs. So the first thing I see is that I have 3 things times each other. And again, I know that I break apart multiplication as addition. So this is where we're breaking it apart. This is the same as log of 3 plus the log of x squared plus the log of y to the 5th. And then finally, if we're breaking it apart like this, we are also going to make sure we don't have exponents. That's going to be something to know. So now I'm going to rewrite it as log of 3. And again, if I have an exponent, that can move to the front of the log. Plus 2 log of x plus 5 log of y. So this will just take practice to make sure that we are simplifying it and breaking things apart as much as needed. For the next one, the first thing I did was I noticed that everything was in a radical, so I changed it to the 1/2. I have a couple choices here. When I did it the first time, I actually just brought that 1/2 out front of the log. But now that I'm doing it again, I'm actually going to use the idea that when I have power parentheses power, I have to make sure I apply that exponent outside parentheses to everything. And then I multiply. So 7 times 1/2, I get x to the 7/2, y to the 3/2. Again, the order that you did that in wouldn't matter as much, but now I need to break it apart as log of x to the 7/2. Because it's multiplication, I add log of y to the 3/2. And last but not least, I'm not going to leave exponents, so I bring those out front. 7/2 log of x plus 3/2 log of y. So this is my final answer here, and there's different ways you could get to that same answer, and that would be just fine. Alright, last but not least, in mathematical terminology, logs are well defined if x x equals y, then log of x equals log of y. Really what we're seeing going from here to here is we just took the log of both sides, which follows a common rule of algebra. We can do anything we want as long as we do it to both sides. And we're going to use that property to solve the following equations. Okay, so if I'm asked to solve something like a 10 to the 10x equals 100, I'm going to use this idea that I'm going to take the log of both sides, and let's see what happens. So if I take log base 10, so log of 10 to the 10x, I can do that as long as I do it to the other side as well. And the reason this helps is if we use our properties. We said if anytime you have a log of 10, log base 10 of 10, that kind of goes away, so I get 10x equals, and now, again, I know 100 is 10 squared, or I could ask myself what power of 10 is 100. The answer to this is actually 2. And now I can just divide both sides by 10. So I get x equals 1/5. So you can see, now that we're getting more comfortable with our exponents, that we are able to use those to solve exponential equations. The next one, if I do logs of both sides, first thing I recognize on the right-hand side is it's 1 over, and we learned that I can do it by taking negative log of 10 to the x plus 1. Now that was a property. Now I'm going to take log of 10 to the x minus 1 on the other side. That was one of our properties, but another way to think about it would have been I could have taken this side to a -1 exponent, and that -1 comes out front. So while it's a property in and of itself, we also know that a negative exponent flips it over the fraction, so we could use that as well. Now on both sides, we have a log of 10, so we can just say that it's equal to the exponent. The difference in the second one is I have to account for the -1 in front, but then I have x plus 1. Now I just do my algebra. I'm going to distribute the negative x minus 1. I'm going to add x to both sides. I get, sorry about that, 2x minus 1 equals -1. Add 1. I get 2x equals 0, divide by 2, so x equals 0. And again, if we continue on, if I log the left-hand side, right now, I'd have log base 10 of 100, so I can't do anything with that, but I do know that I can rewrite 100 as 10 squared, and then if I have power parenthesis power, this is the same as 10 to the 4x. So if I have 10 to the 4x equals 10 to the 3x minus 1, then I am allowed to log both sides. I take log of 10 to the 4x equals log of 10 to the 3x minus 1. I shouldn't say I'm allowed to. I was allowed to the other way. It just wouldn't help me. So now I have 4x equals 3x minus 1. I bring it up here to do my work. Subtract 3x. I get x equals -1. Last but not least, you get to practice a little bit on the other side. And if we apply that same property, so we're still going to do log of 10 to the x equals log of 2 to the 7th. And what we're going to see is that these cancel out. I get x equals log of 2 to the 7th. And we're actually going to leave it in log form, so I'm going to pull that log 7 in front. I get 7 log of 2. You can just leave it like that. So we don't always get a nice neat answer like we did in number 9, A, B, and C. Number 10, we see that if we log both sides, we get x squared plus 1 equals log of 15. Subtract 1. We get x squared equals log of 15 minus 1. To get rid of the square, I square root both sides, and technically when we do that, we get the positive and negative version of the square root of log of 15 minus 1, all under the radical. Last but not least, log of 4 to the x equals log of 5 cubed. The x comes in front. I get x log 4 equals log 5 cubed. Well, we can say 3 log 5 divided by log of 4. So my final answer here would be x equals 3 times the log of 5 divided by log of 4. So that's a lot of different examples of types of things we need to be able to do with the properties of logs. Thank you.